So what we have here is the arc length formula, which is S equals R times theta. So the S represents the arc length. All that the arc length is the distance along the outside of the circle. So think about it as part of a circumference. Okay, so like right here you see in our example they have that portion being S. That is the arc length for this angle. R is the radius of the circle. And then theta is the central angle. And now this theta is in radians. So when we plug that in, it's never going to be in degrees. We can't use that formula if it's in degrees because, again, that's a mismatch. We can't multiply a radius by degrees, but we can multiply a radius by radians because radians are unitless. So what this is, essentially, S is a part of the outside of the circle is equal to the radius times theta. This is just an extension of the circumference formula. Think about what the circumference is. Circumference is a length along the outside that's equal to the radius times 2 pi, because 2 pi is all the way around. Right? So if you think about circumference, we're plugging in 2 pi for theta, and we're finding the circumference. C equals R times 2 pi, or 2 pi R. So it's the same formula. It just works in other situations when we don't want to know the entire circumference. We're just knowing a part of it. So here's our first example. A clock has a pendulum that is 22 centimeters long. So imagine I've got like a grandfather clock. So there's the pendulum, and it is 22 centimeters long. It swings through an angle of 32 degrees. So you know how pendulums swing from one side to the other. Well, its maximum swing from one to the other is 32 degrees. That's freezing cold. Okay, then, what else do we know? We want to know how far does the bottom of the bob travel in one swing. So we're wanting to know this distance here. When that bob swings back and forth, what is that distance? Well, again, you can think about it, that's just a part of a circle. It's a part of the outside of a circle. If that bob would swing all the way around, we would get a circle. But we don't, so we're just wanting to know the circumference of that part, or the arc length of this bob. So we would use S equals the radius, which is 22, times the central angle. Now the central angle, again, has to be in radians. Right now it's in degrees. So I need to convert from 32 degrees to radians. So over here I'm going to do a little scratch work. If I've got 32 degrees, I'm going to multiply that 180 degrees in the denominator by pi in the numerator. So I've got 32 pi over 180, which simplifies to be 16. 8 pi over 45. Yeah. Okay, so now I'm going to plug that in. For the degree in radians. And then I'm just going to multiply 22 times 8 pi over 45. And it'll probably give me an answer that's an exact answer in terms of pi on our calculator. We don't really care about the exact answer right now. So let's round that to 2 decimal places. So you can click the S to D button, and you should get 12.29 centimeters. So the bob travels 12.29 centimeters as it goes back and forth. Any questions there? Okay, the next example. If the bob on the bottom of a 22 centimeter pendulum traces a 9.5 centimeter arc on each swing, through what angle in degrees does the pendulum rotate each swing? So this time we're given different information. It's still a 22 centimeter pendulum, but now we know that the arc length that it traces is 9.5 centimeters. And we want to know what is the angle that the pendulum swings. So this time we're missing theta. So again, plugging into the formula, S, which this time is known, is 9.5, equals the radius, which is 22, times theta, which we don't know. So now I solve, so I can divide both sides by 22. So that gives me 9.5 over 22 equals theta. And that would be in radians, right? Because theta always defaults to radians. Well, we don't want it in radians, we want it in degrees. So normally I would simplify this to get rid of that decimal, but I'm not really worried about that right now. I'm more concerned with getting it to degrees. So 9.5 over 22 is in radians. So I need to put radians in the denominator. So that would be pi radians and 180 degrees in the numerator. And then we multiply that out. 9.5 times 180 divided by 22. And then that's going to be also divided by pi, because this time there is no pi to cancel in the numerator and denominator. So make sure you multiply by that pi as well. And when we do, we should get an angle. I'm going to write it over here. That is equal to 24.74 degrees. Okay, so the next thing we're going to talk about is linear velocity and angular velocity. So if a point is in motion on a circle of radius r through an angle of alpha radians in time t, then its linear velocity is given by v equals s over t, or v equals r times alpha over t. So what does each one of those stand for? Well, v is the velocity. And this is again linear velocity. S equals arc length. T is time. If you use the other formula, R is the radius. And alpha is the angle. Okay, and then just make sure we remember this again. Alpha is in radians. Okay, our angle is always in radians. We can't multiply that if it's in degrees.
Wait, why don't you write across that different things on it? Isn't it the same A?
Yes, that was just a note. The alpha is the angle, but it has to be in radians. I would have probably written it underneath angle, but I didn't have room. Just making sure you know that alpha is in radians. It's a Greek A, it's alpha. It's like a fish. Huh? Yeah, we don't know what they're talking about. Okay, that is linear velocity. We'll talk more about the difference later. The second one is angular velocity, where S is the arc length determined by S equals alpha times R. So Again, that's the same r times theta arc length that we looked at before. We can find its angular velocity by the following formula. So that's omega equals alpha over time. So the omega is the angular velocity. And then the alpha is the angle, t is time. So we have those written from before. So again, I know it looks like a W. It's not a W, it's an omega. So it has like a little loop in the middle of it. But, I mean, that doesn't really matter. So angular velocity is how fast it takes a radius to complete one full rotation of the circle. So, again, think about one of those, playground merry-go-rounds that you're spinning around on. So you've got the bar here in the middle, and somebody's on the outside pulling that bar around in a circle. Well, no matter where you're at on the radius, as that bar is getting pushed around, so say it gets pushed to this point or to this point, no matter which of those black dots you are along the radius, it's going to take you the same amount of time to get back to your original starting position, no matter which black dot you are. So that is the angular velocity. It's how fast it takes a radius to complete one full revolution. Linear velocity is how fast it is at a specific point on the radius. So think about, again, you're on the merry-go-round. Where do you spin faster? If you're on the inside or the outside? The outside. If you think about the middle, you're not moving around near as much. So your linear velocity is slower than if you were on the outside of the circle. Because this is where you get dizzier, is on the outside. You want to get less dizzy, you go to the middle because you're not spinning as fast. Right? So that's kind of how we change angular velocity to linear velocity. So they want us to watch the Rockettes. So give me just a second. Okay, so the first one, what is the angular velocity in radians per second and the linear velocity in miles per hour of the tip of a 22-inch lawnmower blade that is rotating at 2,500 revolutions per minute? Okay, so first we're going to find the angular velocity. So the angular velocity is equal to the angle alpha in radians over the time okay, and the things I know that the radius is 22 inches. And I know that it has done 2,500 revolutions. So what is a revolution? It's a full rotation around the circle. So it's went all the way around the circle 2,500 times. So is that the angle? No, that's just telling me how many times it went around. So think about this. If I went around the circle one time, what would be my alpha? What would be the angle that I rotated? 2 pi. So for every revolution, that's 2 pi radians. So if I did 2,500 revolutions, then how could I figure out my alpha? I'm going to multiply 2,500, the number of revolutions, by 2 pi. So my alpha is 5,000 pi. Okay, now one thing I left out here because they're being real picky on the units. That was 2,500 revolutions per minute. So that means they did 5,000 pi revolutions, or 5,000 pi degrees, not degrees, 5,000 pi radians in a minute. So my alpha is 5,000 pi, but they did that in 1 minute. So I don't actually have to write that down yet. Let's do this. Let's say t is 1 minute. So now when I plug in, that's going to give me omega equals 5,000 pi over 1 minute. So if it asked me what was their speed in radians a minute, I'm finished. But it asked me for the angular velocity in radians per second. So I've got to convert from minutes to seconds. So kind of like what we did before, I'm going to take this value and I want minutes to cancel. So I put minutes in the numerator, seconds in the denominator. That way my minutes will cancel. Have y'all done unit conversions in chemistry? Okay, so that should be familiar to you. You mismatch your units so they cancel, kind of like we did with degrees and radians. Now we come up with our conversion rate. So in 1 minute, there are 60 seconds. So that's my numbers I'm plugging in. So I'm going to take 5,000 pi and divide it by 60. So when I plug that in, again, I don't want to answer in exact terms of pi right now. So I'm going to put it in, then click the S to D button, and I would get 261.8 radians a second. Okay, that was the angular velocity. Now, secondly, it wants us to find the linear velocity. This time we want it in miles per hour. Thanks a lot. So our formula for linear velocity, v equals the radius times alpha over time t. So I still have the same values here. I know that the radius is 22 because we're wanting to find the linear velocity at the tip of, so at the very end of the 22-inch blade. So we would say that the radius is 22. We know that our alpha is 5,000 pi, and that was in 1 minute. Oh, I'm dumb. Hold on. I messed up. So the entire lawnmower blade is 22 inches. Not the radius is 22. I'm glad I looked, or I'd have done. So if the entire blade is 22 inches, then what's the radius? It's 11. Okay. So my radius should be 11 instead of 22. It's my fault. Because the whole blade is 22. So the radius is from the center to the end. So you take half of it. Now we multiply. 11 times 5,000 pi is going to be 55,000 pi. And that's going to be in 1 minute. And what is my units on top? Because this was 11 inches, right? So again, we got to think about our units. So that's going to be 55,000 pi inches in 1 minute. And now instead of inches per minute, I want to make that into miles per hour. So I've got to do my conversion. So the first thing I would worry about is inches. Okay, so I know I want inches to cancel, so I put inches in the denominator. I know inches to feet. I know in 1 foot there are 12 inches, and that will cancel the inches. Now I've got it in feet per minute, and I want it in miles. So can I go from feet to miles? Yes. How many feet are in a mile? Wow. How did you know that? Nobody watches Remember the Titans, huh? That's how you're supposed to remember it. Our feet. So now then we are in miles per minute. So now I need to get rid of the minutes. So minutes is in the denominator, so I want minutes in the numerator. And I'm going to hours. Yep, linear velocity in miles per hour. So in 1 hour, there are 60 minutes. So I would multiply all of this out, 55,000 pi times 60 divided by 12 divided by 5,280. And when you do all that, we get 163.6 miles an hour. Okay. The next one. Okay, it says the blade on a table saw rotates 3,450 revolutions a minute. What is the difference in linear velocity and limes per hour? I don't know how many limes they've got in their hour, but maybe that's supposed to be miles. For a point on the edge of a 12-inch diameter blade and a 10-inch diameter blade. So let's fix that. So it's miles. So both things we're finding are the linear velocity. So I'm going to write down my linear velocity formula. I've got V equals the radius times alpha over t. Okay, so first I need to find the radius. Well, we've got two different radiuses. We're looking at two different blades. So first, let's look at the 12-inch diameter blade. So for a 12-inch diameter, the radius would be 6 inches. Okay, then let's look at the alpha. If it did 3,450 revolutions in a minute, like we did before, we would take 3,450 and multiply that by 2 pi. So 3,450 times 2 pi is 6,900 pi. And then the time is 1 minute. So I would plug all those in. So you've got 6,900 pi times 6 inches over 1 minute. So that would be the velocity of the 12-inch diameter blade. So we multiply that out, we get 4,400 pi inches a minute. Okay, now we would do the same thing, but with a 10-inch diameter blade. So the only thing that would change is our radius. Our radius would no longer be 6 inches, it would be 5 inches. So for the second blade, we would go 6,900 pi times 5 inches over 1 minute. And then when I multiply that all the way out, you should get 34,500 pi over 1 minute. So now I know the linear velocity for both a 12-inch diameter blade and a 10-inch diameter blade. And it asked me to find the difference. So if I'm finding the difference, I'm just going to subtract these two. So I would go 41,400 pi minus 34,500 pi. And when I subtract those, let me write that down. 41400 pi minus 34500 pi. That gives me a difference of 6,900 pi per minute. And that's inches. 6,900 pi inches per minute. And now again, it tells me it wants the answer to be in miles per hour. So I have to convert again. So I've got 6,900 pi inches over 1 minute. I'm going to go from inches to miles. So inches in the denominator, feet in the numerator, and 1 foot there are 12 inches. So inches cancel. And then I'd put feet in the denominator, miles in the numerator. That way feet cancel. And in 1 mile there are 5,280 feet. So now I've got it into miles. And now I want to go from minutes to hours. So I put minutes in the numerator. That way I get my minutes to cancel. So hours goes in the denominator. In 1 hour there are 60 minutes. So we do the same multiplication again. 6,900 pi times 60 divided by 12 divided by 5,280. And when I do that, I find the linear velocity to be approximately 20.5 miles per hour. 24 hours, so that would be my time t. What's the linear speed in miles per hour of a point on the equator of the Earth? So it puts on the equator, so that way it's on the farthest distance around. So we get to use the full radius of 3,950. So we go V equals the radius times alpha over t. So this time our radius is 3,950 miles. Alpha, so it does 1 full revolution. So the alpha would be 2 pi. So we would just do 1 times 2 pi, which is 2 pi radians. And that's going to be over the time is 24 hours. And the reason we stuck with 24 hours instead of 1 day is because we want our answer in the end to be in miles per hour. So this one's nice. It's already in miles per hour when I set it up that way. So I would go 3,950 times 2 pi divided by 24. And when I do that, I get approximately 1,034.1 miles per hour.